Okay, good
Floor
morning.
is yours, Ralph.
Good morning, ladies and gentlemen. Welcome to the RIC Beam Energy Scan seminar series, 5th year running. We are very happy today to have Charles Gale as our speaker. Let me briefly introduce him to you. The main highlights of his distinguished career. He received his PhD from McGill in 1986, then went on for a couple of postdoctoral appointments at the University of Minnesota and Chalk River, before he returned to McGill as an assistant professor, and then quickly became associate full professor and in fact even distinguished professor in 2019. He held a number of visiting professorships all across the world, including Trento, Saclay, Stony Brook, and University of Frankfurt and others. And he has won quite a number of awards and recognitions, including the Alexander von Humboldt Research Award in 2014. And he has been fellow of the American Physical Society already in 2003, in 2007 of the American Association of the Advancement in Science, and most recently he became the fellow of the Royal Society of Canada. And there are other accolades which I don't think I should go into right now. Charles's expertise is broadly speaking hot and dense matter and applications of the ion physics, and I think his seminal contributions in particular concern electromagnetic probes and hydrodynamic calculations, and I think we'll hear about some of them today. So let's welcome Charles and look forward to his seminar. Please go ahead, Charles.
All right, thank you, Ralph, for that generous introduction. Okay, so as Ralph said, I've been asked to talk about electromagnetic radiation in heavy ion collisions, so that's what I'll concentrate on, with some little spin-offs on the way. So thank you again for the invitation. So the outline of my talk is on the screen. So most of what I'll talk about is real photons. So I apologize in advance. I don't have the time really to do justice to virtual photons. So the leptons. That's another talk if you're interested. The photons, I would argue, are unique in our game. They are a special probe because they can be soft and penetrating. That's a combination. Or penetrating probes are hard on some scale. Photons are soft, so they can be both. So the softness means that they are sensitive to the modeling of the relativistic heavy ion collision. So that's also a richness with which I'll try and exploit a little bit. So I'll give you a brief review of the physics involved. I'll talk about real photons. I'll try and put some emphasis on the pre-equilibrium nature of the reaction and how the photons will tell us about that. So that's a relatively new development in our field, I would argue, time-wise. Maybe in line with the topic of this series, I'll say some words about how photons can be extremely useful at lower energies and how photons can be useful in small systems. All right, so the general picture is something we mostly all know. So the standard picture, quote unquote, is the following. We have an initial state followed by a pre-equilibrium state, quark-gluon plasma phase followed by hadronization, and the constituents, the hadrons, interact for a while and then freeze out and then flies to the detectors. And one of the breakthroughs of our field, owing to a large part to many people in this audience, is the fact that the quark-gluon plasma and the hadronic phase phases together can be modeled by relativistic hydrodynamics. That's become a workhorse of the modeling in our field. So let's look at those phases in turn. So there's a lot of work that has been devoted to the initial state, and this work continues. So MC Glauber, followed by P plasma, EKRT is another version of the initial state, where saturated mini jets populate the phase space and then goes over to hydro. More recently, there's some, not quite a version, I don't know that I should call it a version, but it's a flavor of that approach, where you have core coronal effects by the people around Urano. been calculating these things. So all this to say that the breakthrough in hydrodynamics was much enthusiasm, the ideal liquid and so on. But now we're beginning to see that it's perhaps not ideal, which is a good thing. I don't say this in a bad way. But there are non-equilibrium features present at the beginning, in the middle, and in the end. So let's see if we can learn about those. Trento is another model. Effective kinetic theory, I mentioned. IP plasma is being generalized to 3D. So there's a lot of work into this area right now. The hydro part of that, I don't really need to summarize for you. So the field went from ideal hydro to viscous hydro. So the energy momentum tensor is split up into two pieces, an ideal piece and a dissipative piece, which contains shear and bulk viscosities. And the name of the game now is to incorporate shear and bulk viscosities in the calculation and to try and extract this from the data. Okay, fine. What do those quantity really mean? Well, they're a departure from equilibrium in two different ways. So the shear viscosity is a departure from equilibrium in the sense that it's a resistance to deformation. It's really a shear, the viscosity in the shear, as frankly first described by Newton. And the volume expansion is characterized by the bulk viscosity. So bulk viscosity acts as a negative pressure. It slows down the expansion. And there are fundamental property of QCD in the following sense. So you take a box of QCD, you perturb it, it goes back to equilibrium, and that return to equilibrium is regularized, is dictated by those quantities. Cool. Why don't we just calculate them, just instead of trying to extract them from the data? Well, it is difficult. So there are many ways to do this. There's a Kubo relation. If you think that the departure from linear behavior is not too large, you can use linear response theory and use a Kubo relation to calculate the shear viscosity. Here it is on the screen. It is the commutator of the energy momentum tensor, the space-space component. They can be calculated in finite temperature QCD perturbatively using that relationship. This has been done roughly 20 years ago. There's some work to calculate it on the lattice, and there's some reference you can see on the screen. You can use functional techniques, functional non-perturbative techniques like functional normalization group. This has been followed by several groups. Our chair has been doing Schwinger-Dyson calculations to calculate the shear viscosity. And one of the breakthroughs in this field, which brought our field together closer to string theory, was a breakthrough done some years ago, where it turns out that you can calculate what has been claimed to be a lower bound to the shear viscosity divided by the entropy density using string techniques. So ADS conformal field theory techniques. A lot of excitement. Let's try and calculate those, part two. On the left side of the screen, you see compendium of several calculations. So you see calculations using URQMD. Okay, so these are the dots here. Calculations using SMASH. Calculation using holography techniques, calculation using transport theory, calculation using chiral-perturbative theory, calculation using the Boltzmann equation. And the message you get from this is that the answers you get are quite different depending on the technique. So theory-wise, it is poorly constrained. Perhaps you can believe some models more than others. But the general trend of these models is as you rise temperature, the viscosity starting from low temperatures to intermediate temperatures to maybe high temperatures, the trend is to go down, and some curves are flatter than the other. But again, the main message here is that it is poorly constrained by models. And the situation is probably even worse for the bulk viscosity. So we know bulk viscosity is related to the fact that the theory is non-conformal. In a strictly conformal theory, the bulk viscosity would disappear. And the trace anomaly in QCD tells us that the theory is not conformal. So there's a relationship between that general area and temperature and the bulk viscosity. So that has been modeled in the past. And here's one model like this here, where it's modeled on the left-hand side, low temperature side by transport theory, and on the right-hand side, high temperature side by lattice theory. So it goes up as temperature goes up on the left-hand side, it goes up as temperature goes down on the right-hand side. There's bound to be some peak in the middle, and the value of that peak is not well known. It's not well constrained by theory. So all this to say that the information we see as far as the bulk and the shear viscosities go, it is a good idea. It's helpful to model this as best as we can and see if we can get information from the data. And this has been what has been done for the past years. And here's a picture which is on some scale fairly recent in time, but in some other scale, in the sense of the evolution of the theory, it's fairly old. And I'll tell you why in just a minute. So here's a calculation of the multiplicity, the average PT, and of the V2, V3, and V4 using hydro. And you see here the dashed line using shear viscosity, in this calculation, the constant shear viscosity. And the bulk viscosity is the profile we saw on the previous slide. And you see the difference if you have shear only and bulk only. So essentially adding the bulk adds to the entropy. So entropy is related to the multiplicity. And you get an agreement, as you can see here. But the main feature or the main signature of the bulk viscosity, as I said earlier, is a resistance to deformation in the volume sense. It's a resistance to expansion. So there's a direct impact on the average PT. And this is the effect of adding the bulk viscosity is seen here in the solid line. And this is remarkable in the sense of the hugeness or the effective impact it has on the average PT. There's some impact on the flow coefficients, but not so big. And the summary of what we knew, again, not so long ago, is summarized here in terms of the momentum spectra, in terms of the V2 differential V2 distributions at two energies at the LHC, so 2.76 and 5.02. And as you can see from this slide, the agreement is good. But it's so okay. Yeah, I forgot. Should you be interested in downloading music, the hydro code that's used in this calculation? So here's the website. That's my I'm under contractual obligations to say this. So there you go. But there's some progress in the following sense. Our field has turned massively into Bayes analysis techniques, where you actually, which is well suited for many body and many observable environment. And the picture a couple of years ago was done by the Jetscape collaboration, where you can see that the intervals, confidence interval at 90 and 60% are shown on the screen for the bulk viscosity and for the shear viscosity. And this is analyzing a slew of data, building a model, building a surrogate model, fitting data, and using Bayes techniques massively. And the model behind all of this, okay, so again, shear here and bulk there. So the feature I'd like you to remember is that the shear is roughly flat across the temperature spectrum, temperature span shown here. And the bulk viscosity is peaked, as you can see. The peakness, I'll leave you to judge, as a function of temperature. And the model behind this is Trento, followed by free streaming, plus music, and followed by URQMD. On the right-hand side is a more recent development where people have been using not music, but a new hydrocol called trajectum, by a group in the Netherlands. And the picture they get using, again, Trento plus a slightly different version of free streaming, but free streaming nevertheless, followed by not URQMD, but SMASH, is shown here. Probably the main difference is, I would argue that the difference in shear is apparent, but it's not the main difference. The main difference is the size of the bulk viscosity, I would argue, between this estimate and this one here. Let me share with you a more recent development, actually so recent that this thesis was defended last week by Matt Heffernan, where the initial state now is IP Glasma, as opposed to Trento here. So IP Glasma goes into music, goes into SMASH. And Matt did a great job to estimate the bulk viscosity as a function of temperature and the shear viscosity as a function of temperature, using different models for the correction to the single particle distribution functions. So Chapman, Enskog, and Grad. And Matt used Bayes model averaging techniques to combine those to get a 60% confidence interval measure, which you show here in orange. And the light orange is the 90% interval. And so the orange interval here is the 60% interval, the confidence interval for the bulk viscosity over temperature, and the 60% interval for the shear viscosity over temperature. So this is brand new, and Matt's thesis actually features other breakthroughs that are quite noteworthy in my humble opinion. So okay, so fine, but there is more than that. Here's the maximum a posteriori parameters that Matt found for his calculation. By the way, I haven't talked about dileptons and photons. I won't talk about dileptons, as I said, but I haven't talked about photon yet, but they're coming because the modeling of the hadronic phase and the modeling of the photon emission are coupled. You cannot separate one from the other. So be a little patient if you're waiting for the photon part of the story. Okay, so all this to say that Matt was able to get maximum a posteriori parameters for the hadronic part of the modeling. So for example, let me just highlight a couple of those. For example, this is the time switching from IP Glasma to music. Okay, so in Fermi over C, if you have the grad delta F correction, and if you have the Chapman and Enskog delta F correction, and we saw in Matt's analysis that there's not a big sensitivity to the temperature features of the bulk of the shear, of the shear viscosity. So he did two parts of the analysis, assuming that the shear viscosity was flat as a function of temperature, so here and there, and had the temperature dependence that you saw. So not a big difference. Just to skip to the end of the story, Matt cannot tell whether the shear viscosity is temperature dependent strongly or if it's flat. Okay. So tau zero, for example, here's a value of the shear viscosity at the kink. So you model the shear viscosity with a possible minima. I say minima sort of not pretty loosely because these slopes are allowed to vary. So this is the value of this minima, the value of the bulk viscosity at maximum, and so on. Okay, the switching parameter here between hydro and SMASH in this case. So this is what Matt did, and the story here is that he found a weak temperature dependence of the specific shear viscosity and the bulk viscosity, which was incompatible with zero. So statistically, the bulk viscosity is not zero because of this, because of Matt's analysis.
Okay, Charles, there's an urgent question, if I may interrupt.
Sure, absolutely. Yeah, interrupt me because I can't really see the
Okay, so Hannah Elfner is asking if you have an understanding why the bulk viscosity peaks around 250 MeV in temperature, what the underlying physics could be.
That's a difficult question because it, well, I mean, it's of course related. So it's related to, I mean, in the end, it's related to the fact that QCD is non-conformal, of course, but you may be asking what piece of data is driving this. And that's, if that's the question, it's a complicated question to answer because you have to decipher all the analysis. So I don't know which one of those two questions you asked. I don't think I answered either one of those. But at the moment, the message is that it is not statistically compatible with zero. So
okay.
At the moment.
Sorry, yeah. So maybe we can also leave more detailed discussions for later.
Sure.
Thanks.
Okay, so yeah, so here's a feature of some observables that Matt analyzed. So different V2s, V3s, and V4s. Then you can see here actually the not great difference between flat shear and temperature dependent shear. And this is a previous analysis. The SIMS refers to the simulation group of the Jetscape collaboration. So basically, this refers to the Jetscape analysis, which I showed you earlier on in the talk. Same story here for the average PT. The previous analysis is the same SIMS analysis, which you see in dotted here. There's a piece of data that's quite revealing here, is the correlation between V2 and PT, also called rho. So this is measurement by the Alice collaboration, and Matt actually gets this. So this correlation is very sensitive to the initial state. So initial state here is iplasma as opposed to the previous analysis. So again, iplasma is not the be-all end-all, but it's certainly different from the previous analysis. So this is telling us something about the initial state. So Anna, that's probably one answer to your question. What's the difference here? The initial state is certainly different. Okay, so let me go on to photons. Okay, so photons, but I already know that I'll need to skip some parts of this, but okay, what are the direct photon sources? Well, the cold photon sources that exist in PP collision all contribute here. So there's hard direct photons, meaning Compton and QQ-bar annihilation photons, fragmentation photons, and there's the thermal photons, which we've been looking for. Inarguably found, but certainly looking for. If there's a non-equilibrium contribution to the initial state, think core corona, think mini jets. Those mini jets will interact with the particles in the QGP, and will convert. Will produce pseudo-thermal photons. Pseudo-thermal photons because they're not really coming from thermal constituents. One of them is thermal, the other one not. So this is why they're pseudo-thermal or thermal. There's a thermal component. Those harder components, mini jets or jet components, will branch along, and they'll also be a thermal component because they'll interact with the thermal medium, so thermal in that sense. There's a pre-hydro component, and there's a post-hydro component, which is, again, fairly recent in our consideration. Okay, so here's the different part of the modeling again, as seen using the photon glasses. Okay, so there's what we know about the PQCD photons, the very earlier ones, presumably the most non-equilibrium photons of all. And we'd like this to be resting on the flat bed of which is rock, right? Because we want to be able to say that this part is known, let's move to something else. And unfortunately, that's not the case, okay? Because when you do PQCD photons calculation, there are scales that enter the problems. And the scales, there are three of them, right? There's the normalization scale, factorization, and fragmentation scale. And theory gives us no guidance what these scales should be. There's some analysis of sensitivity, scale sensitivity, as done in this very nice study by Patrick Sorange and his collaborators. But if you vary these scales, you get some variation in the direct photon generation, and you get some fragmentation variation as well. If you vary from one reasonable value to another reasonable value. So these are unknowns. They're uncertainty in the modeling. So there's systematic uncertainty in the theory. And by the way, this is another nice feature of the Bayes approach. You can sort of incorporate those in the Bayes modeling. So if you look at the fragmentation component by itself, there are two different fragmentation models here that are featured in this reproduction or PP calculation as compared to Phoenix data. And you see, if you look at the blow-up version here, the inset, there's quite a different value you get by using one model or the other, or a third model here, which is a bit older. So these uncertainties are, again, systematic uncertainties in our modeling. There's a proposal to measure those by some clever experiment using leptons in the initial state some years ago by Vogelsang and his collaborators. Okay, let's move on. Let's move to the thermal part. So let me skip a lot of this story because some of you have heard this and seen this before. So how do you calculate thermal photons and thermal dileptons? They're related to the imaginary part of the photon self-energy, either in equilibrium or not. They can be generalized to the non-equilibrium domain. I'm using Schwinger-Keldysh, for example. So Schwinger-Keldysh calculation have this contour, which has two parts to it, part 1 and part 2. And this is the photon self-energy calculating using those techniques. They've been calculated up to next to leading order in finite temperature field theory. I'll show you some results in the next slide. They've been calculated on the lattice for dileptons because time-like correlators are easier to calculate on the lattice, and they've been calculated for hadrons. Some years ago, it has been found that there needs to be some sophistication involved in looking for even leading order photon spectra calculations, because there's some collinear singularities that enter the problem. And these collinear singularities have been tracked down by Amy, Arnold, Moore, and Yaffe just about 20 years ago, and been isolated in a very nice series of landmark papers. So the photon production rate is known to leading order in alpha S. They've been calculated at next to leading order in alpha S. And this is, again, some calculation that has been done more recently, okay, maybe 5-6 years ago by these people here. And the calculation involved two pieces going at next to leading order. These Amy rates involve a scattering kernel. So the scattering kernel needs to be calculated at next to leading order. And this was a breakthrough done by Simon Caron-Huot, who's a couple of doors down the hall here. He did a calculation using OPE techniques some years ago. And this very nice paper was used in this generalization. And these people also calculated the larger angle epsilon that's associated with next to leading order photon generation. If you combine these sophisticated techniques to ask yourself, what's the change in the photon emission rate? Actually, it's not that big. It's something like 30% with a reasonably large coupling. The coupling that's associated with phenomenology at RIC, for instance. And if you use a smaller coupling, the situation is even less difference between leading order and next to leading order. So all this to say that the previous calculations are not in parallel, but they're more precise because of the next to leading order estimates. You can do calculation using kinetic theory, and this is shown here. So let me briefly go over this by just mentioning that those have been done. And once you do those, you can actually incorporate viscosity. So these photon emission rates have been corrected for viscosity. So here's another connection with the non-equilibrium part of the spectrum. So the non-equilibrium part of the spectrum is being calculated on one side by sophisticated Bayes techniques, and you get at eta over S and bulk viscosity, and you incorporate those in the photon spectrum, and they do make a difference. And here's the summary of the photon spectrum and V2 as of just a couple of years ago, or a few years ago. So Phoenix data, 0 to 20%, 20 to 40% centrality. V2, Phoenix, shown here, and Alice shown down here. So sorry, this is Phoenix on the top side and Alice on the right side, so on the bottom side. So Rick on the top and LHC in the bottom. And the data is in red for Phoenix. It's in green for star. So there is a difference between Phoenix and star, and I'll come back to that in just a minute. And the sum of the contribution you see in green here, and the thermal part is in blue, and the prompt, okay, PQCD part is in dotted line here. So at high PT, it's dominated by prompt, and there's a thermal component that shines at low PT. And the same is true at the LHC, but the agreement at LHC is, quote, better, unquote. And well, it is, you see it here, so you can make up your own mind. V2 is shown here, and the V2 at Rick is shown in green. Okay, what is shown in blue is the thermal V2, but the thermal V2 is brought down by the PQCD V2, which is basically 0. And here's a story at minimum bias. Okay, again, Phoenix and star. And here's star only in different multiplicity. Okay, so the story at Rick is summarized here. There's the difference between star and Phoenix, and the star agreement you can see by yourself. Okay, some of the recent developments. So the recent developments have been in pre-equilibrium photons. What do I mean by that? Okay, so there are sort of bookend photons, okay, in the beginning and in the end. Okay, so pre-equilibrium will sit here, and there's also post-equilibrium, if you wish, late stage reaction contributions to photon production. Shouldn't those be included, you say, in what I've told you already? Yes and no, and I'll tell you about that in just a minute. Okay, so the pre-equilibrium evolution. So just before the hydro, there's been some development, and several calculations by several people. Let me show one here. This calculation is dubbed compost. So initials of the people involved, and some O's judiciously or not inserted. So what these people did is the following. Okay, so you take effective kinetic theory approach, so a Boltzmann approach shown here. And it would be nice to solve the Boltzmann equation in general for all time and see what you get. But the Boltzmann equation is difficult to solve in practice. It's 6 + 1 dimensions, and it's prohibitively, it's computer intensive for one thing, and it's just difficult to solve. And people have been trying to do this for some time. And this is one attempt, a very clever attempt to try and circumvent a total solution to the Boltzmann equation. So what these people argued is the following, is that, for instance, if you take this effective kinetic theory simulation, the Boltzmann equation, for instance, and look at what happens between a given instant in time and some instant in time later, arguably, if you look at what happens at this instant in time, if you look back in time, the zones that could have influenced it are limited because of causality. So what these people identified practically is some region that could influence the region forward in time, okay? And identify the causal circle in this two-dimensional picture, but it's more than that, in more than 2 dimensions. So they've identified the causal circle and averaged over it. So this is shown here as the average energy momentum tensor, and allowed for fluctuations over that causal circle. And the fluctuation is calculated using linear response, okay? So this is what this group of people did. And the breakthrough, in the sense of practical breakthrough, is that once they did this, they saw that you could actually propagate the linear response from one delta t, from one instant in time, one position in space to the next position in space, position instant in time, using Green's function techniques. And it turns out that the Green's functions actually are remarkably robust. They don't depend that much on where you start and where you end. So you can actually compute them once and use them for a variety of circumstances. So that's what makes this approach very practical. So it is a breakthrough in theory, in the sense that it's a way to look at the problem. It's also a breakthrough in numerics, or a way to solve this problem. So what was done here is to start from the initial state, which was IP plasma, insert compost in the middle, and then let this follow by hydrodynamics. And what was found by these studies is that the effective kinetic theory provides a very nice bridge between the initial state and the hydro phase. And the bridge is actually quite robust in the following sense. They did a simulation which involved not IP plasma, but some free-streaming stage. IP plasma is not that different from free-streaming, but they involve here a free-streaming stage, followed by this effective kinetic theory, followed by this second-order hydro, and looked at several variables. And here's the energy density, normalized by the energy density, the ideal energy density. And they saw that if you varied the strength of the coupling in the kinetic theory part of the calculation, there's not a big difference, actually. It doesn't matter that much. It's very robust to variations in scale. So it's very suggestive of something like an attractor. And this provides a very appealing bridge between the very initial stages and the hydro stages. So the story that was done by our people, our group, was to say, well, let's look at two scenarios. Let's look at the standard quote scenario, where you have IP plasma in the initial state, followed by hydrodynamics, followed by transport. Compare this with the one I just told you about: IP plasma, compost, hydro, and transport. Okay, so this means, that's another way of saying it. You take the T mu nu from IP plasma, you give it to compost, you give it to hydro, and then you give it to URQMD. Just a side remark, compost, again, is conformal, and it's gluon based. Okay, it consists of gluons. Okay, fine. So let this come back. We'll come back in just a minute. This is what we get for hadrons. Okay, so I'll leave you to look at this collection of results. Phoenix, LHC at 2.7, and LHC here at 5 TeV. The spectra, the average PT, and the V2, and V2 and V3 and V4. So the short version of the story is that the spectra in the V2 are somewhat insensitive if you have compost or not, but the PT actually can tell. If you have compost, you have the dotted line, and if you don't have compost, you have these full curves here, which deviate from the data at some starting in the peripheral region. Okay, fine. Should you trust the hydro as in the peripheral to high centrality regions? The answer is probably not. But what causes this this deviation? And what causes this deviation is that when you insert compost, you rob the evolution of some pieces of hydro, which is not conformal. The hydro has a bulk viscosity. So you substitute for that bulk viscosity a region which is conformal. And what that non-conformal bulk viscosity does for the reaction is that it slows down the reaction. So it brings the PT down. Now you don't have that situation anymore. But compost is appealing theory-wise because it does provide a bridge between the very initial stages and the hydro stages. So there's some good and bad things of it. But the message, I would argue, is that, okay, so here's a summary of what I just told you. But the message is that to get compost to agree with the data, you have to change the bulk viscosity. What that means is that the bulk viscosity is actually very sensitive to, well, it's sensitive. You can see the sensitivity here, right? So here's eta over S, and here's the relaxation time. I haven't talked to you about that. I don't really have the time here, but here's eta over S rather, zeta over S, sorry about that, bulk viscosity over entropy and density, with compost and without compost. Okay, so there's a sizable difference here. And this is a good thing. That means that the transport coefficients are sensitive to the early time dynamics, and the photons are sensitive to the early time dynamics as well. In this model, what's the sensitivity of photons? Okay, there's part two of the compost story for photons, because I told you that compost consists only of gluons. So no quarks, no photons. No quarks, no dileptons. So how do you put back the quarks in compost? Well, there was a chemical analysis here done by those people using this effective kinetic theory. Again, sort of in the same effective kinetic theory that sort of rests behind or below composts. And they saw that effective chemical equilibrium was achieved over some period of time that is shown here. And then this period of time is quite robust, again, with respect to variation in the partonic cross-section. And similar studies were done previously as well. So what we did is to model this, and we inspired ourselves from these studies here and said that, okay, let's calculate the photon production rate and let's multiply it by suppression factor. Suppression factor meaning that chemical equilibrium is not achieved in the early times, but it is achieved as time progresses. So physically, what does that mean? So physically, you can imagine you have a medium that's gluon dominated. Gluon fusion will produce QQ bar, and then Q will interact, and the Qs will be present, and so on. So what initially started with gluons only will populate the quark phase as time goes on. Okay, and this is a curve that just says what I just said in word. And we've allowed here for some leeway and for some liberty in how fast this is achieved. Okay, so there's a chemical equilibrium time here that's 1 Fermi and say 1.5 Fermi. And what that does for photon spectra is shown here. Okay, so Phoenix and the LHC. And there's not a big difference certainly on the log scale, whether you have instant chemical equilibrium that's achieved over 1 Fermi or 1.5 Fermi, but you can see a bit more here if you normalize these curves on a linear scale to the one that's instantaneous. Okay, so 1 Fermi is in red, 1.5 is a little below. Okay, and for different centralities, this is shown here. And at the LHC, it is shown here. And if you look at what it does for data, okay, so the pre-equilibrium component with a chemical equilibration time of 1 Fermi is shown in yellow. And at RIC and at the LHC, it is, I would argue, barely seen, but it is just quote unquote, seen, or it does contribute at the close to 10% level, I would argue. What about the V2? Okay, so presumably the V2 will be affected, and it is. Okay, and it is in the opposite way, in the following sense. If the chemical equilibration is later, V2 is larger. How's that possible? Well, if the photons appear later, the flow has time to develop. So V2 is larger. So here's what happens here at the RIC, and here's what happens at the LHC. And I'll leave you to judge the agreement with data. And I would say that the photon flow puzzle, which some of you know, most of you know well about, is more of a puzzle, a trick, than it is at the LHC. Okay, because at the LHC, the spectra is not in disagreement in some modest language, and you can see the agreement with the flow. Brand new data from Alice at 5 TeV. So here's the spectra. Here's the calculation I just told you about in here. Some other calculations, one by our chair and collaborators, another hydro calculation, a calculation by a model called PHSD. And the data cannot really tell between these different calculations, but it is certainly on the verge of being able to. If you look at the data on a linear scale and normalize with respect to this calculation by our group, which was done very kindly by the Alice collaboration and shown in Quark Matter 2022, so brand new, preliminary, you see the agreement of the data with the model. Okay, and you see Alice at 0 to 20%, 2.76, 5.02. Okay, so new calculations in red. Okay, so the new measurements in red. You can see here that you only have upper limits in the very low PT for the time being. Another technique shown in blue by the same collaboration. So I'll leave you to just a few more seconds because this is brand new. Probably most of you haven't seen this yet. Okay, so let me tell you two other parts of the photon story. There's another pre-equilibrium contribution I haven't really talked about. If in the early stages, mini jets, okay, so there'll be a non-thermal part of the parton spectrum that is from the very, very early stage. One way to think about this, if you want, is the harder part of the shower from the very first interactions. So there's mini jets, okay, and those will exist in nucleus-nucleus collision as they exist in PP, measured in PP. So they can be modeled. So what was done here is to say, okay, let's take the mini jets provided to us by Pythia. Let's put them in Martini, which is a model that combines the jet physics with the hydrophysics of music. And let's look at those jet photon conversions and Bremsstrahlung. So the photons that are associated with those, quote, jets, unquote, and the more thermal medium, although we know now that it's not really thermal. And this is summarized in this plot here. So here's the prompt contribution, the very, very cold contribution you've heard about early, and it's dominating at low PT. And this for at least photons at 2.76. And the conversion contribution, the new one, is shown in black, and the Bremsstrahlung contribution is shown in red. There's a pre-equilibrium contribution I just told you about by compost, shown in green, and a thermal contribution, which is important at lower PT, but it rapidly dies. If you go from low PT to intermediate PT, and at high PT, it's basically gone. If you take the channel over the total, it's from medium PT to high PT, it is dominated by the prompt contribution, but there's some 10 to 20%, well, actually I say it here, 30% at 4 to 5 PT related to those conversion and Bremsstrahlung contributions together. Okay, so those mini jet contributions or core corona contributions in some other language, contributions to photons, pre-equilibrium contributions are not small. How not small are they? Well, you can see it here. So with and without is red and dark green, I guess. Yeah, dark green, shown here and on the log scale. And here's the data over theory plot, with and without. So with is certainly different from without. There's some in the calculation. There's some uncertainty. You can't really tell them apart statistically for the moment in these calculations, which are done by. I should have said this. And if Ruse is listening, I apologize. I had this on a previous slide. This is Ruse Moderazi Yazdi, who's a PhD student here, who does these calculations. So what Ruse finds is that these jet medium contributions are not dominant, but they're nevertheless important. Okay, so that's for the first part of the bookend photons, the earlier part. What about the later parts? So what was done here, let me tell you in just some words, what was done in the photon calculations using the hydro calculations that I've shown to you in the past. Up to very recently, except for maybe for the PhD calculations, photons were not calculated in the later parts of the reactions using macroscopic model. Why is that? Well, because if you want to do this macroscopically, you have to run the calculation for a long time, just because the photons are produced with alpha. And alpha is small with respect to alpha S, so there's a statistics issue, and that can be circumvented now with calculation techniques we have, so we can actually get around that. But you have to calculate this reaction by reaction. So you have to calculate the cross-section for photon emission in pi goes to rho gamma, and pi rho goes to pi gamma, and all these possible combinations. And this again is being done, and that's been done mostly in the work that I've shown to you earlier on by several people. And this work is now being incorporated in these final state cascade calculations. But this implementation in the cascade calculations is fairly new. So what people did in the past is to take the hydro and to run the hydro down to a slightly lower temperature. So you saw through Matt's analysis that the preferred map values, the maximum and posteriori value to switch from hydro to smash in his model was around 150, 145. So what people did in the past is to say, well, there's a part to the photon generation story that is lower in temperature than that. So let me actually run down the hydro to something like 120, 110, and not use that part for the hadron simulation, but use that part for the photon generation. Mind you, the hadron generation at those low temperature, what was done in the first generation hydro calculations some years ago. Okay, so all this to say that this is a calculation that shows what happens when you do implement these reactions, photon generation reactions in a cascade model, in a reaction by reaction dynamical model, which here is SMASH. So the first step in this implementation was to say, well, let's implement those in SMASH. Let's implement pi goes to rho gamma, pi rho goes to pi gamma, which are very important at intermediate PT. And let's implement this in SMASH, and let's compare this with what happens if you do this in a box. And let's compare SMASH in a box with hydro, which is an equilibrium, a model more suited for equilibrium than SMASH. But SMASH is equilibrium if you put it in the box and let it run for a long time, which is what is done here. And basically what this is comparing is that it is the calibration step of this story. So SMASH over the theoretical expectation is shown here, and it agrees. So the implementation of those microscopic reactions in SMASH and the hydro, they agree. So SMASH and hydro talk the same language. Okay, so let's do what I just said. Let's calculate the photon generation in the later stages with SMASH. And let's compare with hydro, but run at a lower temperature. And this is shown here. This is the photon spectrum calculated using hydro stopped at 150 MeV. Hydro stopped at 150, then switch over to SMASH. So what would be the proper thing to do if you believe Matt's analysis? And the older thing to do, if you take the hydro, stop it at 50, and then don't stop it. You run the hydro past 50 down to lower temperature. And it turns out there's not a big difference. So this approach, and it's you see here on the linear scale. And the band, the hydro band, is that if you stop it at 140 and if you stop it at 120. And if you take the music plus SMASH story, which is right in the middle, suggests that running, as far as the photon is concerned, running the hydro to this lower temperature was actually not a bad thing to do. It didn't quantitatively, if you want to be really precise, then arguably you should do the most correct thing is as far as we understand it now. But were we grossly wrong? As far as the spectrum is concerned, the answer is no. V2 actually there is some interesting difference. And I think we're just beginning to understand this difference. And I say beginning to understand because this is still need to be explored. So the story here tells us that if you run the hydro to these lower temperatures, you get this band. So there's some V2 certainly observed here. And if you show, you show it here actually, if you take the music and stop and you SMASH at some intermediate or low value of PT, there's some difference, okay? This difference is not completely under control in the sense that we know that it's due to the fact that SMASH does the right thing. That is, it is a statistical model, so it does kinematic decoupling. Okay, so the particles decouple by their own. You don't need to do things like Cooper-Frye, for example. It depends on the nature of the cross-section. So there's some dynamical decoupling that's provided by SMASH. So that's one part of the answer. The other part of the answer is due to our analysis. This only includes a few channels. Okay, what I mean here is the following. This only includes pi pi goes to rho gamma, pi rho goes to pi gamma, and pi pi epsilon. Those are important numerically, but it's not the whole story. So the whole story will follow. So the message here is that if we include what we think is a more complete dynamical model in the end, we get something that is not unlike what we did in the past, but not the same either. So there's some map to understanding the data, which is again becoming a lot more clearer. So I think I will need to skip. Let me. Can I have a few more minutes?
Sure.
Okay, let me just tell you this part of the story, which I think is very interesting. So lower energy, okay, so lower energy, which is maybe in line with the series of this seminar. So what happens if you model lower energy collisions? Here's a picture in eta, and this corresponds to high energy on this side and lower energy on this side. So the span of eta, okay, so the space-time rapidity spanned by the higher energy is much larger than it is at lower energy. That's not too surprising. But you see here the temperature, and the temperature is higher in the middle than it is in the end. Again, not too surprising. But if you look at the chemical evolution, so mu b divided by t, the story is the following. So let me just put a mark here at 1, and let me put a mark at 3 to give you small and larger scales. At higher collision energy, okay, so you see it is sort of, it goes as the inverse of the temperature. Okay, so temperature is high in the middle and low in the end, and it's the inverse story for the baryon chemical potential. It's low in the middle and high in the end. And the difference becomes smaller and smaller as you go from high to low to low energy, excuse me. So there's a big difference in the modeling here as well. Why is that? Because as you model these things, the overlap time is a lot longer for low energy. Okay, the overlap time is the size of the radius actually. So it's not almost instantaneous like at high energy. There is a finite time for the overlap, and it's shown here. So you can see here that at high energy, it's actually very small. And as you go to lower and lower energy, PA and AA collision, it actually becomes quite large. So there's a challenge for the theory. The challenge for the theory is to model these early parts. Okay, so here's a model that I'm going to tell you here. So the model is essentially developed in this paper here by Chun and Bjorn. And it shows the following. So what they do is to say, okay, well, there's a nucleus-nucleus collision. Let me draw a string between them, and this string will decelerate the nucleons. And the time for deceleration is a parameter of the model. So you create this string and it decelerates the nucleons. And after a certain time, which is a parameter of the model, the energy in this string is given. So the lost energy, the lost kinetic energy, if you wish, the lost kinetic energy is fed into the hydro as thermalized, and where the endpoints are fed into the baryon density. So this is what I just said in words is shown here in equations. And what shows the difference between the high energy part, where the difference, the population here is almost instantaneous. And you see this curve that's familiar to most people here, the tau Z curve, okay? Which is essentially one value of series TZ, sorry, which is essentially one value of tau. You see here a population in T that extends to an amount that's not small, okay? And in tau eta space, there's a big spread when around eta is equal to 0. And the story here, when there's correlation between eta, the space-time rapidity, and the particle physical rapidity y, and the correlation tells you that if you go from central to more forward or backward rapidity, you also probe times that are later. Okay, so this will be important later. So this model is tuned to charge particle distributions in rapidity space and PP bar net baryon distribution in again rapidity space. And you can judge by the quality agreement yourself. It's actually not perfect, but it's not bad either. So, but those are just words. You can see how good it is looking on the screen. Okay, so what about the photons? Well, the photons at finite baryon, the mu b will increase the photon rate at low momenta because of the distribution functions. And this has been known for a while and studied by in several papers. And it has been shown if you have partonic photon generation, so parton generations as calculated earlier on, and parton and hadronic generations in the later reactions at lower temperature. So there's some increase whether you have 0 or finite baryon number, 0 and finite baryon number. I'm shown here for some value of temperature and baryon chemical potential divided by the temperature. So there's some increase that's on the order of 50 to 60% for those parameters, and also in the hadronic stage. Okay, so the low collision energy will affect the dynamics of the population, the formation, the feeding in the hydro, and the low kinetic energy will affect the evolution of the baryon chemical potential and the photon generation rates. I just said that, and here it is. Okay, so what happens as far as the dynamics go? Okay, so the dynamics will look something like this. So this, the picture at high energy, almost instantaneous population, the picture we're used to seeing through the work of Bjorken and collaborators, and this dynamical feeding in. Okay, there are several ways to do this, and there's several models now that do this in a slightly different fashion. So we're quite not at the quantitative level yet, but qualitatively, things won't change that much. So instantaneous deposition, or the earlier way of doing it at high energy, shown in dotted line, and the dynamical deposition here. And the story here is that the cooling and the feeding in happens later, because the hydro is populated gradually, as opposed to at high energy. That's the big difference. So what does it do for photons? So here's the thermal photon spectrum. So if you do instantaneous energy deposition and dynamical energy deposition. So dynamical energy deposition will affect the spectra in the high PT region the most. Why is that? Well, because the medium in the hydro is fed gradually. And as this time evolves, okay, you get more and more hydro, the scales of the energies go down. Okay, so the energy scale goes down because the nuclei are stopped in general, and the energy scales go from large, as they were through the very, very first time they collide, through later in the collision, they go down. And the effect that this is mostly shown in the high PT part of the spectrum. So what this will do is that the dynamical energy deposition, so the gradual feeding of the hydro, will affect mostly the high PT part. This heightening of the low PT part is not really shown here. You don't really see a 40 to 50% difference, which, mind you, was only for one value of the temperature and chemical potential. But if you fold in the chemical potential evolution and the temperature evolution, not the big difference in the low PT version, but in the low PT part of the spectrum, but a much harder, bigger difference in the high PT part. The big difference is in the V2. So instantaneous energy deposition is in dotted, dynamical in the full curve, at 0 in forward rapidity region. Quite a big difference in V2. Okay, so there's the V2 will show quite unambiguously the dynamical energy deposition model here. Again, why is that? Because the photons happen later in this dynamical energy deposition approach. They happen later, so later flow has time to develop. So they happen later, more flow. And the photons see this and they report this. Okay, so this is quite exciting, I think. And this will be measured at FAIR, will be measured elsewhere. The caveat here is that you need to have a PQCD evaluation at those lower energies. So as you go lower in energy, PQCD calculations become harder and harder in the sense of less trustable. So having a measurement of photon production in PP is invaluable. That's true at all energies. We only have one measurement at RIC. So this is true at all energies. PP production of photon is invaluable. Measured. Okay, so let me skip the small system part because I'm running out of time. So let me give you a conclusion. So the conclusion is that photon can be soft, yet tomographic. Only variables we have like this. They reflect the modeling of the matter we have, and this modeling is continuously evolving, and this is shown in this latest analysis, I would argue. And we're moving together towards ab initio modeling, which is very exciting. Lower energy, fascinating part of the story. And I didn't talk, unfortunately, about the electrons. I didn't talk about magnetic fields. I didn't talk about many things I didn't talk about, but let me just concentrate on the things I did talk about, and let me thank you. Thank you.
Thank you very much, Charles, for this beautiful, in-depth, yet very pedagogical talk on the recent development.
Sorry for dragging, sorry.
No problem. So there was one question from Uli Heinz, which he asked during the talk, but wanted to only come up in the discussion, which is now. So he asked on slide 9 that there's a
Can I ask the question? I would like to phrase it a little bit more broadly.
Oh yeah, sure. Go ahead.
So thank you first of all, Charles, for a wonderful talk over an enormous amount of work that has been done in this sector, and all the different approximations that you try to change in your modeling and how they affect the observables and so on. And some of that is already feeding back into the Bayesian analysis, which tries to infer the parameters, the quark-gluon plasma that we are mostly interested in, their viscosities, as shown on this plot. But what this plot also shows is, depending on which modeling framework you use for doing the dynamical modeling, you get different posterior probability distributions for these inferred parameters. That suggests that there is significant influence of these model uncertainties that you pointed out throughout your talk on the inference for these parameters. What's your point of view of where we stand with respect to quantifying these modeling uncertainties on the inference, and what do you think needs to be done to put this on a solid ground?
Yeah, okay. I think we're getting there. I think there's some progression here. Probably the way these plots are arranged. There's some progression in this, going to that, going to this. Again, I don't want to offend anyone. This is not the point here. This is just my point of view. So I think there's some progression in this, in the sense that here is Trento, and Trento is a very elegant model that is a significant improvement over MC Glauber, in my view, in the sense that it's flexible and you can get some mapping between the influence of the overlap functions, for example. Trento does a great job of trying to extract the dependence on these from data. But there's some drawback to Trento, and the plus side is that it is very elegant and very malleable and very polyvalent. So that's the plus. And the negative is that Trento provides you little dynamics. It doesn't give you flow. There's no flow in Trento. So you have to supplement Trento by something that gives you flow, and it's a very sensible thing to do. It was this flow part was provided here by free streaming. Free streaming is analyzed also in this work here, but free streaming collides with hydro because, again, not to offend anyone, free streaming, the mean free path is infinite. In hydro, if you think of ideal hydro, the mean free path is 0. So you go from free streaming to hydro, and there's a collision in theory. So, okay, fine. This is partly alleviated by providing some dynamics by IP Glasma. Is IP Glasma the final answer? And the answer is no, because of the drawbacks. Some of them I pointed out immediately in the talk, rather. But IP Glasma is okay. The dynamics there, the flow dynamics is provided by the Yang-Mills equations. Is that the final answer? And the answer is no, because Yang-Mills is not that different from free streaming. So I would argue that the evolution in our understanding and our modeling sophistication is shown here in this order. And then there's compost. So
okay, but may I interrupt you there?
Sure.
This is a way of presenting it which puts in theoretical priors. You have the prejudice, let me phrase it somewhat provocatively, that IP Plasma is a better model than Trento. Therefore, what I see there in the bottom, I should weight with higher confidence than what I see at the top. To what extent can you quantify that? To what extent can you actually show that the Trento the IP Plasma induced collision description works better across the board than the other one? And can you quantify that? And can you include that in a quantitative way in your posterior distribution for eta and zeta?
Yeah, actually, okay, that's a very good question. I mean, that's a very good way. Let me just correct what you said. It's better in the sense that iplasma, Trento has no dynamics, iplasma has dynamics. So that's the better aspect. And does it have the final dynamics? And the answer is probably not. Okay, so let me just quantify what I mean by better and worse.
Yes, I understand your definition of better. It's a theorist's definition of better. I would agree with that as a theorist. Yeah. But is it better in describing the data?
Yeah, actually, that's I should have brought this with me. The difference between Trento and iplasma is chapter 2 of Matt's thesis. So again, I don't want to be glib, but he did some analysis which shows some observables which are radically different in Trento and in iplasma, and those are related to correlations. And again, that's not too surprising because Trento does a good job for one-body observables, but if you look at correlations, it does have correlations, and iplasma has correlations as well, but do they have the right correlations? So that's what Matt looked at, and the conclusion there is that iplasma does better for those correlation observables. So
okay, very good.
That answers your question, but I'm afraid I should have shown these plots here. But since that was not the goal of the talk, that's a slightly different talk.
Thank you. So let's have another question at Shuryak.
Hi, Ed. I have two comments, Charles.
Yes.
One is about what you spoke in the middle of your talk. In early 90s, me and Xiong had this hot glue scenario with exactly this idea that you first have gluonic plasma. And if you have gluonic plasma, you don't have photons and electrons. So there were several papers there, yes? It's precisely the idea you're discussing. Yes?
Yeah, that's exactly correct.
Yes. Now the second comment is related to this slide 9, which was just before, and the question of Ralph. The question is, what happens? Why temperature like 250 is somewhat special? And that precisely, if the early plasma is mostly gluons, we know that in pure glue theory, critical temperature, which is first order transition, is 270. And from study of topology, etc., we also see that about 270, 300, even in QCD, there is change, significant change in non-perturbative physics. So this early non-equilibrium stage, which lack definitely, because we know initial state is very much gluonic, and creation of quarks take time. And if it is not quark-gluon plasma, but mostly gluon plasma, it has different dynamics. That's a very important thing. That's all.
Okay, so your question is, why is this region here so important?
Oh, on the left, look at the left, for example.
This region there?
Left plot?
Oh, no, on the left picture.
Oh, this is the plot here.
Yes, Ralph asked why there could be a peak at 270. I was saying pure gluon plasma has strong first order transition at that temperature. So if we think of early plasma as mostly gluonic, we should think of that.
Okay. Actually, that was a question by Hannah Elfner, which I just read, but okay.
Okay, sorry.
Yeah, yes. Okay.
So, okay, yeah. Sorry.
That's a very interesting question. Yeah. Okay, let's move on to the next question then by Rob Pisarski, please.
Hi, thank you, Charles, for an excellent talk. I was going to answer, make a comment on Hannah's question and on Edwards as to why the apparent form of the bulk viscosity is peaked at relatively high temperatures. And there are three contributions to the breaking of conformal symmetry. One is the restoration of chiral symmetry, which is mainly due to quarks. The other's the rise in the Polyakov loop, which with temperature, which is mainly due to gluons. And the other is the trace anomaly, the energy minus 3p. And for lattice indicates with dynamical quarks that the peak at e to the minus 3p is about 200 MeV. And if this result is correct, it suggests that the quarks play in the restoration of chiral symmetry a rather small role in the bulk viscosity, and that it's basically driven by gluons through e to the minus 3p and the increase in the Polyakov loop, which agrees with Edward's comment, although I would demur from him in that in pure gauge, it's a weakly first order transition, but that's a rather beside the point. But I just wanted to say in agreement with Edward that it's basically gluonish. It's driven by gluons. Thanks.
Yeah, no, I don't disagree. No, I agree.
Okay, very good. Govert Nice has a question.
Yes, more of a comment that actually on the same slide, slide 9, that we in fact have a newer Bayesian analysis that came out in June, where we're now quite consistent also with the bottom picture. So basically the main difference between, well, at least the main difference causing this, for example, this negative slope of the eta over S seems to be the nucleon width. So in the new paper, we fitted to the new Alice measurement of the lead-lead cross-section. And if you include that measurement, you decrease the width that Trento assumes for the nuclei, or for the nucleons, and then the eta over S slope immediately becomes like negative, as you also find in IB Glasma. And also with the rho observable, we find similar agreement now to Alice.
Very good. Just as a question to you, since you're there. Hi, by the way. You still use Trento free streaming and?
Oh, yeah, I should actually say that that's, I've put that in my quark matter talk, but the paper that is out doesn't include that yet. We actually generalize free streaming to incorporate like some sort of interpolation between free streaming and ADS-CFT. And of course, as you said, like the free streaming has infinite length, the infinite mean free path, and ADS-CFT has like 0 mean free path. So you get this, and actually it prefers the ADS-CFT value. And we hope that that paper will be out soon, where we actually explain that in more detail.
Okay, thank you very much. There's a question by Oscar Montero. Can you state it yourself, maybe? Or I could read it, but.
Hi, sorry. Sorry, can you mute me there? Sorry, I was just thinking about what Edward was saying before, and give me a second. Can you just disconnect it? Just disconnect it. All right. So I was thinking about what Edward is saying, right? And like the thing is that, like, I mean, this gluonic system is out of equilibrium. It's completely out of equilibrium right in the beginning, and it only starts hydrodynamicizing. sorry, give me a second. We have a second computer here. It's acting out. Okay, so and it starts hydrodynamicizing only when quarks can come in. This has been shown by all these kinetic studies, right? So like when we talk about this peak and how and why it's there, it's actually, I mean, it's very, it seems like it's an interesting point, like, to say that the transition actually happens at 270 MeV, like if it was a first transition with only gluons. But it seems to me that it actually goes against what we kind of know about the equilibration of the whole system, right? Like, I mean, we cannot really talk about this as if it was an equilibrium state, right? When, I mean, because of how we see this evolution happening, actually. So
can I comment?
Sure, go ahead.
Yeah, people who do these models, they treat glue, they have perturbative models,
think
kinetic model with scattering, etc. In this model, whether it is in equilibrium or not in equilibrium, there would be no phase transition. It's a very primitive model. Yes, lattice is in equilibrium, but then it has no non-perturbative physics, which is, I think, much more important. In other words, kinetic theory uses some absolutely arbitrary cross-sections, which were calculated in perturbation theory, which we know from many other quantities are wrong. And they don't have phase transitions whatsoever. So we don't really trust them very much. We use them to model, yes. But
Okay, very good. Nushu has a question.
Yeah, hi, Charles. Thank you for the very nice talk. I also have a question on this slide. I ask
There's no photon here.
I have two questions on this. One is, you see this error band is vary from different analysis. My question on this is, are this error band dominated by theory uncertainties, or is dominated by still experimental data? So that's question one. Question two is, when all these plots only happened in the QGP part, the temperature large higher than 150 MeV. What happened for other side? Let's say below phase transition side. Is there anything we can do? We can analyze to extract the information. So yeah.
Yeah. Well, okay. So let me answer the second part of your question. On the other side of on the low side of the temperature spectrum is these calculations. So those calculations attempt to calculate eta over S, for example, on the low side. Okay, so then you have, that's the second part of your question. On let me go back. Yeah, so is the band dominated by theory or experiment? And the answer is yes. So again, I don't want to be glib, but the way this works is that the posterior is there's some theory prejudice in the sense of choosing your posterior, and the theory prejudice, that's not a good word. The theory prejudice means that there's a window in which you think the answer will lie, but you want this window as wide as possible, and you want this window to create a model for you that will address the data. So as you take this posterior window and you compare with data, this band narrows and narrows and narrows. And this comparison with data involves the theoretical, experimental uncertainties as well. Okay,
let me. I have to.
Let me finish my story. So this is a combination of both. Okay, this is a combination.
No, each one of these plots, the uncertainties are entirely dominated by experimental uncertainties. The theory is taken as a given, and given that theory, that theoretical modeling, you extract the posterior distribution for the viscosities.
But that's what I said. That's what I said.
So for each one of them, it's entirely.
Do you want me to give this talk or not?
Go ahead.
Okay.
Sorry, go ahead.
Sorry.
So that's what I said. I mean, the theory prejudice is in defining the posterior. Okay, that's what I mean. Okay, period.
Okay, any more questions? If I may, I would have a question concerning also, in fact, here the issue of the transition to hadronic matter, in particular the transport. It seems to me the eta over S values where this is done are relatively low. That may still warrant, as you also discussed, a hydro treatment from some point of view, as opposed to a transport treatment where on the next slide I see, for example, we see that SMASH has a rather large eta, or next slide, where you show the eta over S values. So for example, here, SMASH seems to have a rather large eta over S. So, so it seems you're switching to a transport code which mismatches sort of the eta over S that you extract.
Yeah, no, that's absolutely correct. That's absolutely right. And this currently is something we need to address. Everyone needs to address this. This is not the emphasis of any calculations I know of. That's absolutely right. When you go from the hydro to the microscopic model, the inherent values of the transport coefficients can be different. Okay, and this matching is not done in great detail. Absolutely right.
No, I very much appreciated your discussion later, where you sort of re-invoked the scenario to run the hydro all the way down to the freeze-out or close to it, and it seems to have some robustness. But yeah, very good. Maybe Hannah wants to comment on that.
Yeah, just quickly, because actually, when you look at this plot on the upper left there, you see that there are also transport calculations, which is these points, these purple points and the green squares that actually give a rather lower value. And actually our current SMASH versions have more or less actually that behavior. So that doesn't, I'm not saying there's no discontinuity, and there's certainly a difference also between the viscosity that we extract there in a box, right? This is SMASH in a box. This is not SMASH in a dynamical evolution. So I think this makes a difference again. And we know that there are other discontinuities in terms of physics that we're making at this transition. But just saying, if you look at these eta over S plots that we calculated in the current version of the model, they are actually much lower than this value, and we're working on getting this out also, that you have this.
So what is the difference? Is it in the
difference is the cross sections.
No,
it's the question of how many elastic cross sections you have compared to how many resonance cross sections you have.
So you changed the cross section.
We just added more channels that you have to add, and these are just elastic cross sections that we added, and this is the main difference. And this is actually this physics is described in this paper that is referenced here, or actually paper is not really referenced, but there is a paper by Jean-Bernard Rose where we explain this in all details, where the physics difference comes from between the upper lines and the lower lines. And this is really the difference if you go via resonances, which takes some time, or if you go directly via elastic collisions. That changes shear viscosity a lot in this region.
Okay. Yeah, one more question by Uli, maybe.
Sorry, yeah. First, Charles, let me apologize again for cutting you off earlier. That was not the way to do it. But I would like to make the point a little bit more clear, so that you seem to say we are saying the same thing, but I don't think we are. So when you show these plots here, they are the result of trying to solve the inverse problem. You start from the data, and then with some dynamical model in mind, you reconstruct, infer from that the parameters of the model. And you do that. Bayesian statistics is a method that allows you to do that in a principled fashion, where you understand very clearly where all of the uncertainties come from. And in this case, the model is implemented through a prior assumption, and that is either the model on the left upper corner, or the model on the right upper corner, or the model on the lower upper corner, but not all of them taken together. That means in these plots, the uncertainties that come from the modeling are not included in a principled fashion. They are not consistent with the rest of the Bayesian analysis. And that is, I think, what is still missing, and that is something that we as a community have to work on.
Okay. You would like to comment on that?
Since we're having a friendly discussion. Again, the model uncertainty, I would argue, are partly based in the choice of priors. There are analyses that were done in the past with some priors that excluded regions in phase space because there were quote theory reasons to believe that the regions in phase space would not be accessed, and I would argue those considerations were wrong. I don't like people saying that people are wrong in the past, but there's some theoretical considerations in choosing the priors. That's one thing. And the model uncertainty, since we're talking about this, is partly addressed in the way Matt did the analysis on the bottom. so here's a way of addressing model uncertainties. We're considering model uncertainties in the way Matt did the analysis is to consider base model averaging. So what he did is to say, okay, there's a model that exists, and let's say that the non-equilibrium corrections to the distribution functions are Chapman-Enskog, or let's say they're grad, two ways of doing things, which address the same physics in a slightly different fashion. And let's weigh these models by the Bayes evidence. So this is the Bayes model averaging that he reports. So the model differences in that sense, or the model discrepancies or similarities, depending on how you see it, are addressed here in that sense. There's model averaging that is done in the way I described it. So that gives you an idea of the model differences and the model uncertainties and the model systematic uncertainties.
Very, very good. So when you talk about priors, you mostly talk about prior assumptions for the parameters in a model. But
Yes.
in this, whereas when I talk about priors, I include the prior choice for the model in that. So that's
Okay.
why we may have been talking a little bit past each other. But
Okay.
you're right. So when you take the lower right model, it's not. I misspoke in the sense because I didn't realize that this was included. So it's not one model, but it's several models which differ in the way the particleization, the fluid is particleized. But it's one model in terms of how the dynamics is initialized, what the initial conditions are, and what the pre-equilibrium dynamics are. And the two other models at the top are different from that model also in that. So they correspond to different priors as far as the choice of the model go, and to include the effect of this model choice in the prior on the inferred parameters is something that is not yet fully systematically and done in a principled fashion.
Yeah, that's correct.
Okay, so let's settle that question then. And I don't see any more questions. So that leaves me to really thank very much Charles Gale for this, as I said, in-depth yet very pedagogical, inspiring talk. Thank you very much, Charles. And everybody have a good rest of their day wherever they are. Bye.
Thank you.
Thank you. Goodbye.